Welcome, everyone. I am absolutely thrilled to have you here for this explainer. Today, we're diving into what I honestly consider a masterclass in modern security architecture. We're going to break down exactly how to build an AI-driven, fully autonomous application and infrastructure vulnerability management framework. So if you've been trying to figure out how to actually harness frontier AI to secure your enterprise pipelines and truly automate risk management, you are in the exact right place. All right, let's just jump right into it. Here is our structural blueprint for today. We're going to cover the cybersecurity moment, architecting autonomous remediation, protecting enterprise data, guardrails and human oversight, and we'll wrap it all up with a highly actionable 12-month implementation roadmap. All right, kicking things off with Section 1, the cybersecurity moment. Let's be real for a second. The arrival of ultra-large frontier models, like Claude 5 Mythos and Fable, into our core engineering suites has permanently broken traditional point-in-time scanning strategies. To really grasp why this is happening, just look at legacy static application security testing, or SAST. It relies heavily on abstract syntax trees. It basically strips your code down into language-specific structures and hunts for deterministic signatures. It's literally like proofreading a massive book purely for grammatical syntax errors, but remaining totally blind to the actual plot. Because it evaluates these trees in complete isolation, it misses all the modern business logic abuse and complex multi-repository configuration flaws. Frontier AI, on the other hand, plays a completely different game. It processes your code structures by projecting functional tokens into a multi-dimensional semantic vector space. So instead of just checking rigid grammar rules, it's actually analyzing the context, the architectural intent, and the logical execution behaviors across your entire multi-file architecture. And this is exactly why legacy tools absolutely choke on modern cloud architectures. Think about it. Cloud-native environments are highly asynchronous. They're event-driven. They're constantly passing variables across message queues and distributed handlers. This generates massive mathematical path explosions. When legacy tools try to track these infinite state variables, they just fail. They literally have to limit their scanning depths just to keep the system running, and the result? False positive rates frequently exceeding 40%. At that point, you're not getting actionable security alerts. You're just getting an inbox full of pure noise that your engineers are actively ignoring out of sheer alert fatigue. That brings us to Section 2, architecting autonomous remediation. If we want to move past the cognitive speed limits of our human engineering teams and shift our primary metric from time to detection over to mean time to remediation, we need to deploy an autonomous software remediation engine, or AXR. Take a look at this sequence. Notice how this specialized multi-agent mesh forms a completely closed-loop system right inside your private enterprise parameters. It discovers, it isolates, it tests, and it patches, all in a continuous, active flow, rather than just acting as some passive warning siren. So how does this actually work? Let's break down the exact workflow of this 4-agent tag team. First up, the discovery agent. It's constantly evaluating pipeline code changes to map out deep structural anomalies. Second, the validation agent catches those findings, spins up an isolated sandbox, and actually crafts an exploit payload to see if the flaw is genuinely reachable. Third, we have the patch synthesis agent. It reviews the source code, trace logs, and, crucially, your own corporate coding standards to generate a syntactically precise code update. And finally, the QA validation agent applies that synthesized patch back in the sandbox, reruns the exploit, and hits your global test suites just to guarantee the fix works and introduces zero regressions. Now, I want to emphasize that the real magic happens right here with the validation agent. It essentially acts like a relentless automated pen tester. By dynamically building an exploit string inside an ephemeral container, it physically proves that a suspected remote code execution vector is a true positive before it alerts a single human being. And if the exploit fails because of some upstream restriction, it just logs it as mitigated. This right here is exactly how you completely eliminate those 40% false alarm rates we talked about earlier. Moving right along to Section 3, protecting enterprise data. Obviously, if you're an enterprise or a SaaS provider, you absolutely cannot just pass raw proprietary code, IP, or live tokens to public APIs. Doing that completely shatters data sovereignty and regulatory compliance. No way around it. The solution here is deploying a privacy-centric security proxy engine. Think of this as your inline perimeter defense. It sits securely inside your enterprise borders, acting as a hard cryptographic boundary. It guarantees that you maintain strict GDPR and CCPA compliance while still letting you tap into the massive reasoning power of external multi-tenant AI clouds. If you follow the mapped route here on screen, you can see exactly how this protective shield operates. As your private code repository tries to send data out, the proxy engine redactor steps in and intercepts it.
It automatically rips out high-entropy secrets and connection tokens and swaps them with randomized placeholders. At the exact same time, it obfuscates your core functional names and internal URIs, building an in-memory translation map locally. Then, the multi-tenant AI cloud processes that anonymized data, synthesizes the patch, and sends it back. Finally, the proxy reinjection core reverse maps those original identifiers before securely committing the pull request. The beauty of this? Your secrets literally never leave the building.
To actually pull this off, you need to enforce a strict zero data retention, or ZDR, checklist across your API connections. But you might be wondering, okay, if we strip out all the context, how on earth does the AI write an accurate patch? Well, we solve this through localized contextual retrieval augmented generation, RAG. By standing up localized vector storage layers, think tools like Milvus or Qdrant, using open weights embedding models entirely inside your private cloud parameters, you seamlessly inject your necessary internal coding standards right alongside the anonymized prompt. You get all the deep context without any of the broad exposure. Okay, let's pivot to Section 4, Guardrails and Human Oversight. So, with the AI handling all these routine detection, verification, and patch generation loops at blazing machine speeds, traditional ticket triaging basically disappears. But humans, we're not going anywhere. Look at the trade-offs on this matrix. This shows how your engineers evolve into strategic guardrail engineers and invariant architects. It's all about knowing exactly when to let the machine run loose. For rapid code triage and patch synthesis, you absolutely want fully autonomous code injection. The MTTR is sub-minute, fixes happen instantly. But for branch promotion to mainline, human-in-the-loop GitOps review is 100% mandatory. Yes, it takes a bit longer, but the operational risk to your core business logic stays minimal because your senior architects are manually peer-reviewing system impacts before anything merges into production. Looking at the enterprise scaling infrastructure here, you've got the strategic governance layer right at the top. These are your human architects coding the invariants and defining the error budgets. Right below that, you have the AI, which is running the autonomous compilation and testing plane. And at the foundational level, holding the whole shebang together, is your production telemetry guardrail fabric. It's really this perfectly balanced ecosystem of human strategy and machine execution. And that telemetry fabric is governed by a super strict autonomous error budget policy. We are absolutely not blindly pushing autonomous updates globally. Instead, synthesized patch updates are routed first to an isolated infrastructure canary tier, which is processing maybe just 1% of your production traffic. If your real-time observability mesh detects even a slight spike in error frequencies or request latencies, bam, the autonomous rollback loop triggers immediately, instantly restoring the last known secure system baseline. This right here is why your engineers can actually sleep through the night while the system patches itself. All right, finally, Section 5, your implementation roadmap. Here is a very specific, highly tangible 12-month project plan to actually roll this out in your enterprise. Phase 1, months 1 through 3, you're focusing purely on deep local ingestion. Deploy your on-prem vector storage grids and build up your localized embedding context without a single asset ever leaving your trust boundary. Phase 2, months 4 through 6, is all about closed-loop sandbox validation. Get those ephemeral container runners deployed and have your validation agents executing dynamic exploit payloads in a staging environment. Phase 3, months 7 through 9, you flip the switch on automated patching. Let the agent grid actually construct code repairs and feed them directly into your developer review streams as Git pull requests. And Phase 4, months 10 through 12, is your progressive production rollouts. Connect your deployment targets, lock in those localized error budgets, and activate the automated canary rollbacks. Listen, by following this framework, you aren't just plugging in some fancy new tool. You are fundamentally rewiring the entire DNA of your vulnerability management pipeline. You are shifting your organization from a state of constant passive reaction right into an era of active, autonomous resilience. These frontier AI models, they're here, and the architecture to harness them safely is already proven. So the only real question left for you is, are you ready to transition your security team from exhausted ticket triagers to strategic invariant architects? Thank you so much for joining me for this explainer. I really hope this blueprint serves you well as you build out your own frameworks. Catch you next time.